What's going on? It's about, what time is it? So we're gonna do a short hour-ish stream here. Uh, hour 30 minutes-ish, hour 30 minutes-ish doing some reading. Going to try and read two chapters on, excuse me, one on algorithms and architectures for digital processors, perhaps the most important chapter yet in this book. And second, another very important chapter on the design of ALUs and just more generally arithmetic units. As before, every time I say like or filler words, this is $3.20 to open source. Um, Perhaps we'll figure out what project we're doing later, but just generally, perhaps to do the Gleam compiler. But yes, so I'm gonna read this. Gotta pay attention. Gotta not get caught lacking and fall asleep like I did last time. Audio. Quickly check the audio. Hour 30, but yes. Sounds acceptable. So yeah, I'm gonna read this, gonna get a water, grab something to eat. But yeah, let's do it. I'm gonna take my glasses off. I'd really like to finish this book. Maybe like 2 chapters a day in the next few days, perhaps like Wednesday. And yeah, I just gotta. So I kind of figured out like what I really need to do this week. Finish the Gleam dependency issue I was working on a few streams ago. I need to finish DMAWeb, write an itch parser in Haskell, do the presentation, set up the IP networking cores, and yeah, so if that sounds like a lot and borderline impossible, it's because it is. So let me stop messing around against morning. Water being a Lagunitas IPNA. Tell me that's not crisp. Does that come through how crisp that is? Look at that. If you don't think that's crisp, can't help you. I'm about to mute my mic while I murk these pretzels, but you know the drill. That one's off, bro. There's something funky in that one. Вода лучше. Alright. So yeah. Short contrast of FPGAs and ASICs. Look, I've read a few of those in this book. So nested loop programs exist and can be represented with a DFG. Language parsers extract a DFG from an NLP or from an HDL-based behavioral description by analyzing the activity flow of the statements within the lifetimes of the variables. So you have this loop that has these two loops that do these 2 to 4 loops. So a DFG is a directed acyclic graph. Where's the F come from? What is called a? I swear I've heard DAG before. Oh yeah, I'm a bit dumb. We already defined that as a data flow graph. We have vertices and edges. Each vertex represents a functional unit, FU, which operates on its inputs to produce its outputs. Functional unit might consist of a single operation or a more complex ordered composition of operations, in which case the functional unit itself might be represented by a DFG giving a fine-grained view. So all the edges, ij, originate at a node, terminate at a node. Given an edge, the data produced is effectively piped to the next one. So a data dependency exists between a pair of nodes corresponding to an edge if the functional unit uses the results so any useful edge is going to define a data dependency. So it reveals the producers of the data, the order of its flow. It also exposes parallelism, which reveals opportunities for concurrent computation and has implications for the lifetime of variables. The designer's task in general is to transform the DFG for an algorithm into the structure of hardware. And you can use this data path control separation. So given that the control unit must control the data path, the initial task is to specify an architecture for a data path unit, which, if controlled to respect the constraints implied by the DFG, will implement the algorithm. And the control unit controls the data flow. So beginning with the graph, the high-level synthesis task of data path allocation involves transforming the DFG of an algorithm into an architecture of processors, data paths, and registers. From these, you can synthesize a RTL model from Verilog. You have three ways to kind of split up functions into subfunctions across cores with pipelining or in parallel. System C. So let's consider the design of a halftone pixel image converter. So we have this Floyd-Steinberg algorithm. Converts an n by m array of pixels into array black or white pixels. So it appears that you kind of alias any error to neighboring pixels. So a pixel receives a distribution of error from its 4 neighbors. And you calculate the halftone pixel value based on it. At each pixel location ij, a weighted average. Weighted, I imagine they're all weighted equally. I suppose they're not weighted equally. Interesting. Where so you weight the errors at the 4 neighboring pixels. CPV, did I skip what CPV is? Corrected pixel value. So CPV is the PV, so what is PV? Pixel value, probably pixel value, plus the average error. Then we round it to 0 or 1, according to a threshold. So where it's max, 255 with 8 bits, the threshold is 128. The main array of nodes is isomorphic to the array of pixels. Similar in form. That makes sense. And you have all these arrows denoting the dependency. Perhaps dependency is not a good word there because it's not actually your time reliant, as this will come in at once. But you're still dependent on the values to derive the CPV from the EF. So these additional nodes have no functionality other than to initialize the computation. So you have some outer ones. Okay. Makes sense. The algorithm will execute in n by m time steps, with each time step including time to retrieve and store data. So you can express it in C as, so you have this 2D array. K0 is all 0, 0k is all 0, and then the writer boundary is 0. And so for each pixel in here, compute the average based on these weights. Add that to the pixel value to derive the calculated pixel value. Round it, make it a 1-bit thing. And the error, CPV minus CPV round. Not sure why the error is CPV minus CPV round and not EAV. But I think the point is made as to the basis is set to imagine the 3 ways to parallelize this or to break down this DFG. Quick stream check, looks good. Okay. There are various options for forming a hardware implementation of an NLP realizing the image conversion output. The FU are combinational in nature. It's isomorphic to the DFG. Pixel processor data path unit are given below. It's hardware intensive and structural. systolic array. What is a systolic array? Set of identical FUs with high connectivity. Of 48, I should have just continued reading. 48 identical processors hardwired for the data flow. Cycle time will be limited by the long path. Implementation is synthesizable as combinational logic and requires no control. Test bench produces the sharp contrast image patterns shown in figure 9.6. The graduated ones and 9.7. So this looks like no pairing, and this looks like some halftones with this weight. And a cursed waveform. So the module is implemented. Takes in 48 pixels and 6 HTPV rows. Its output is so it has 8 outputs. One to 6, that's 6 outputs. Sorry, these are all outputs with this size. These are all inputs with this size. And you have these wires. HTPV row. You have 48 error 8-bit wires. So you have a lot of hardware. And so the calculation itself is quite short. So yeah, it's extreme hardware performance. Currently execute in a single long clock cycle and require no memory and no data path controller. The NLP itself suggests another alternative, a level-sensitive behavior that executes the NLP. It's given below, synthesizes a combinational logic, converts an image in time t baseline, and the system clock must have a cycle time greater than t baseline. So we have similar inputs. So we have some reg for the CPV around EI. So we have this threshold here, these error weights, that's sum to 16. So the difference in our algorithm, so the real concern, is that we're breaking it in by row. So this is like the parallel setup. Break them by row and calculate the averages. Though, how does it get from I from a difference in the j-axis? W1 minus 1, so V2 times 0, 0. Okay, so it looks at row 0. So it looks at the row before, at the ith position, okay. Then the 8th one. The 6th one looks at the row above the 5th position. 5. Okay. The NLP for the image converter also suggests a synchronous implementation. So the architecture will require memory, but releases the resources while the prosecutor design would use a single FU to convert the entire image in 48 clock cycles. Naive alternative is to write a single synchronous cyclic behavior that describes the NLP of an algorithm, but a synthesis tool will create an architecture. Really? Machine of a model when its algorithm and style is given by an image convertible one. Verilog does not have randomly accessible two-dimensional arrays. It requires a separate array of words in each row of pixels. Orders the rows sequentially within more floor loops. The assignments of variables are made within the procedural assignment, are made with the proc s assignment operator. The order of the statements reflects the data dependencies. The time delays reveal the evolution of the computations. They're removed after debugging and before attempting synthesis. So this is a test bench, I imagine. he used like the DOIs things. The signal goes asserted to launch the image converter. Done. When it's done, reset flushes the memory. So here's our new output called done. New reg called done. Go clock reset. Waits. Accumulator. What do you call those accumulators? Not really. You have n by m with this threshold. Wrapper for synthesis. Reset begin, reset action done. So this is resetting. And this is the init. If go begin wrapper. So you have these artificial delays. 20. Compute. Same logic as above. Image converter. So we 3200 clock cycles. Re5, invert the clock. Re50. Gonna reset 100, reset 1. Go 0, then go to 1. 10, reset 0. And initial begin go. Go is 1 for 100 cycles, and it goes 0 for 100 cycles. Begin, image pattern, and image pattern. Initial fork. So set these signals as such. Image converter 1 cannot be synthesized. That's this. That makes sense. So we can have a concurrent algorithmic state machine with a data path. It's like the alternative. Shaded region defines a computational wavefront. The locus of DFG nodes that can execute concurrently. The wavefront indexes partition the temporal domain and identify clock binaries. Graph of those are resources required by a synchronous machine. That would exploit the parallelism. So you need a more complex controller to do this. The architecture of the machine's data path will be designed to exploit the concurrency that is evident. It will pursue by manual methods what a behavioral synthesis tool should accomplish. So where's the alternative? So let's see this. You have a pixel memory unit taking in the 48 pixels. And you have 4 pixel processor data path units. They're taking in a amount of pixels, turning 2 of them. You also have a control unit that takes the current index 28. 28 is indexing into. What is the 28 bits indexing into? Division table for mapping DFG nodes to time slots. 1, 2, 3, 4, 5 processors. 3, 4, 6, 7, 8. 9, 12, 12, 13, 14. 15, 16. 17, 18. Yes, I've done. Reset. Go. Body image. Notes. 48 is at 1. Okay, so let's go back and read this. A machine with the wavefront indexes would require a maximum of 4. Take 18 time steps. The inputs of each processor provide the value of the pixel at the location indexed by the indicated by the address passed from the controller, and the arrows at the locations of the pixel switching neighbors. The controller is implemented as a sequencer, which creates the addresses of the pixels that are to be updated in a given time step. The entire array is downloaded to a memory unit in a single clock cycle. Now that you know that you need at most 4 FUs, you have a reservation table which shows one of the many possible mappings that know that the DFG to a set of 4 processors that exploit the concurrency. Space-time partition on which every node has a unique processor. Time slot here. So this pipelining is an opportunity to stream images with a throughput of 12. But memory cannot be selectively loaded to partially update its contents. Image converter, you have all these signals, outputs, the 8 bits at each of these, done. Oh, I'm done. HTPV is halftone pixel values. There's 8 of them in each row. Yeah, okay. So this waveform. Not too worried about that. So you have these wires. So you have this memory unit. Has all this in it. PB control unit. Takes in an index. So 6448. Why do you need a 24-bit index? Audio image, audio eyes, done. State, next state, index. Parameters. So if reset. If it's state or go changing, don't want values, next state is to a state. If it's idle and go, S1. Okay. If you're in the first 18 pixels, or if you're in the first 18 states, add 1. Otherwise, you're done. Go to idle. And if state or go, begin done. Yeah, done is 0, index 0. How do you move this 0? Index is 0. Where's index 0? So case state 60 0 D. So these are 18 states, and you have these pixels that can be co-processed. The data path unit hardwired for 8x6. So there's your 8. There's your weights. Oh, okay. Your weights. No, these are weights. There's your threshold. EAV is the computation. Right shift by 4. CPV is PV plus EAV. CPV round is CPV less than threshold, so that rounds it. HPTV handles that again. Error handles that again. pixel memory unit. So this has similar inputs. You can just apply them from this. So on index 1, beginning. So if the index is in the first 8, it's 15 and 16, do this. It's 23 and 24, do this. Index 2, index 3, index 4. See, I'm not sure what this, I don't remember what these indexes are. I think I'm fine there. That is a lot of Verilog design trade-offs. So here's your trade-offs. So in the baseline, there's no memory. The baseline execution time. 48 times time FU. 12 times TFU times 12 times TFU. Not synthesizable. Streaming the images because that's the buffer size. Okay. That was a bit complex to me. Like, I didn't care to understand everything about that. But I think that's okay. So it did not have feedback. If it needs feedback, require memory. Bubble sort. In pseudocode. So this is like a naive 1-by-1 comparison sort. Yeah. So we have this DFG. B. So I and J. 2 adjacent numbers. So you have J minus 1 and J. So we swap these, so this is like a swap. So this is like a swap right here. So we're starting on the right, we swap those. So you're starting on the right and bringing it left, so okay. You go to 5, we bring it there, 6, we bring it there, okay. So the functional unit swaps. The DFG employs swaps to implement the NLP. DFG has feedback because contents of a memory cell can be written back to the cell. Presence of feedback implies data storage. If the loops of the NLP are unrolled, we get the temporal DFG shown in 916. Must occur on a separate clock cycle for the data to be fetched, transformed, and written. The shaded nodes in memory cells indicate the data paths that are exercised during a given step. The structure of the DFG for the bubble sort algorithm suggests that a baseline implementation of the machine consists of a single FU that executes repeatedly with different data until the algorithm expires. The ASMD chart implements the baseline architecture. It's a bank of N registered holding the words, 2 counters, inner and outer loops. So here we have a Verilog implementation of bubble sort. I never thought I'd be looking at a Verilog implementation of bubble sort. So parameter A 18283. So these are the values. Word size. You have this array. You have these wires. 4 bits. Times 8. 4 bits times 8. So if it's idle, module T bubble sort. Remove this for synthesis. Civility begin. Listen to data path T bubble sort. Actual fork. Huh. So if we're running, j is greater than I. Next state is running. Decrement j. If greater than, swap 1. Else if I is less than n, can run and set j to I. Okay. Else idle. Idles. J passage clock reset. With OD load. Reset. Huh. Okay. DSPs. Shannon's sampling theorem states that a band-limited signal can be recovered from its time domain if it's sampled at a frequency greater than twice the highest frequency in a spectrum. Oh yeah, I saw that. I heard that, but I didn't understand why that was the case. One hertz. 1 hertz? That's trash. So DSP is characterized by the above. Another ASIC FPGA comparison. Operates synchronously on fixed word samples, regular intervals. Mac. This is like an intro to DSP. Can be analog and sampled. Then it's binary fixed word. Could be corrupted. Need to be filtering. Remove noise. The design must consider finite word lengths that result from the representation of these signal samples, the weighting coefficients of the filter, the arithmetic operations performed by the filter. The operations of a DSP unit can be distributed spatially or temporally, depending on if it's one or multiple. So in the former case, it's an entire word. Latter case, it's a word in each clock. Distributing operations over the temporal axis. Higher throughput. More latency. Non-casual filters. Called moving average filters. Wait, this is kind of crazy. Right. What am I trying to do? 200 megahertz. It's millihertz. Am I dumb? 200 megahertz. The period is this is kind of embarrassing. Oh my gosh, dude. Dude, I low-key need freaking King Henry died by drinking chocolate milk, bro. Mega. We're too far beyond that, bro. Oh my god. Metric units. So if it's 200 megahertz, then millionth, it's gonna be 5 nanoseconds. Each clock cycle is 5 nanoseconds. Dude, I'm dumb. That's actually so dumb. Is your weights? Data out is equal to data in times plus the weights times the samples. What's samples? Where's samples defined? Samples is a reg of 1 to order. Order is 8. Samples are 1. It's data in. Then you shift the samples in. You move the samples up to the order. Why does my water smell like fish, dude? So IR is the same, but you have feedback. So you're also adding in some weights on the previous values. So these are your feedback filter coefficients. So you add the feed forward with the feedback. Integrators. Running sum of sample values. Integrator par, below, describe the integrator related by. So yeah, an accumulator. It's accumulating things. And here it is. Carry shift reg. Data out, shift reg. This project is super difficult. Like if you haven't taken 22, and not so much 2200, definitely 2110. If you haven't taken 2110 and you don't know Haskell, and you haven't read at least like 3 books on this topic, because you kind of need this. And this. Or, I didn't commit it yet. And this. And the prior one. You kind of have no idea what's going on. I mean, even I have an incomplete idea what's going on. So here we're writing, sorry, a byte sequential integrator. Successive bytes or data in within 32-bit words are accumulated. Word length latency 4, data in, data out. Hold, OSB flag. Shift reg, word length times latency minus 1 to 0. Reg carry, word length. It's the sum. So shift reg. So if carry, just can keep them the same. Then if not, then it's the positive edge of the clock. So we're doing Shift drag, we're putting in shift word length. So this is like the aliasing or the sign extending thing. We're sign extending it by the shift drag, word length, wait and see, -1. Word length, so -1, okay. And so we're shifting it. And we're putting in the sum of the word length -1, 0. Sum. Shifting in the sum of these bits. And that's the data in plus shift drag, wait, see word length. Data out. Shift drag. Latency times word length. -1 to latency -1 times word length. So these are the leftmost. How does that work? $1,024, 2,046. Did out 1. So it's pipelined by 4 clocks. It's 4 clocks behind. Differentiators is a measure of the sample to sample change. Backward difference is implemented with a buffer and a subtract. Differentiators. So what does this do? This is like the change. So it's put on a data out. So buffer, data in. Data out. So wire, it's equal to data in minus buffer. Decimation and interpolation are sample rate conversion filters. Sample rate conversion filters, yeah. Decrease, interpolation, increase. Decimation, decrease, interpolation, increase. Shannon sampling theorem says that a bandwidth signal that is sampled at a higher you recovered from the samples. Why is that the case? What is the intuition?
This video is sponsored by Brilliant. Here is a cosine function with a frequency of 1 hertz, and I am going to sample it with a frequency of 7 hertz, meaning I'll have 7 equally spaced snapshots of the function essentially every second, if we think about the x-axis as time. Now, if I take away the original signal and just handed you these samples, and I told you the original signal was a cosine function with
Oh,
of 1, and it was
that just came out.
7 hertz. So you know mostly everything. Could you then determine what the original signal was? Or asked in a different way, are there any other sinusoids that would have these exact same values and thus would look exactly like this if sampled at 7 hertz? Well, our original signal with a frequency of 1 hertz of course contains all these samples. Now, if we plot a sinusoid with a frequency of 2 hertz, notice it does not contain all these samples. Neither does 3 hertz or 4. But once we hit 6 hertz, all the samples line up with this new function. The same thing also happens at 8 hertz, 13 hertz, 15 hertz, and infinitely many more. So you could not tell me the original function if I gave you these samples, because all the other information is lost, and you'd have no idea whether the original was this, or something else. It could technically be anything that goes through all these sample points, but if we stick to just sinusoids, then you still have unlimited choices. However, notice that 1 hertz, the actual original signal, is the lowest frequency that you could guess. If we go down to anything else like 0.5 hertz, this clearly will not go through all the samples, and nothing below 1 hertz will. Now, if we go back to our original 1 hertz signal and sample it a little slower, let's say 4 times per second, well, now the same thing will happen, but at different frequencies. These samples correspond to our original 1 hertz signal, but also a 3 hertz signal will go through all these points. Same with 5 hertz, 7 hertz, and all odd numbers. You could guess any of these from the samples given, but 1 hertz is still the lowest. However, going back to our original signal, something happens when you take the sampling frequency below 2 hertz. Let's say we sample at 1.5 hertz. Now, if I gave you these samples, there are still infinitely many other sinusoids that could contain these, like one with a frequency of 2 hertz or 2.5 hertz. But now another sinusoid that works is one with a frequency of 0.5 hertz, which is a lower frequency than our original signal. So of the infinitely many correct guesses you can make, the original is not the one with the lowest frequency. In this case, there is one option lower. This change happens when your sampling frequency is less than twice the frequency of your original sinusoid. The original was 1 hertz, meaning you need a sample at more than 2 hertz, or you'll get this issue. What we just saw is basically the idea behind the Nyquist-Shannon sampling theorem, which says you have to sample your signal at a rate faster than twice the highest frequency in your original signal to avoid distortion. This is why, for example, when I open Audacity to record this video, there's a preset to a frequency of 44.1 kilohertz. That number is slightly more than double the maximum frequency humans can hear, 20 kilohertz. So here's where that comes from. Sine waves have frequency domains that just look like this. These 2 spikes really represent one single frequency, that is, the sine wave itself. But most other functions, like a sinc function for example, have a continuous spectrum of frequencies that make it up. But now if I sample our signal, what are the frequencies that make this up? Yes, as in what sine functions make up a bunch of samples, or spikes? Well, I'll just tell you, the answer, and I'm going to make some room here, is you just take the original frequency domain function and make copies of it around integer multiples of the sampling frequency. So if we were sampling at 7 hertz, then this would be 7, and 14, and so on, both positive and negative. And we do this forever. So the frequencies that make up a bunch of samples is this here. That's weird, and it makes sense, because the Fourier transform that calculates a function's frequency domain has this really nice property that it works in reverse. The Fourier transform of a sinc function is the rectangular function, which means the Fourier transform of the rectangular function is the sinc function. Technically, applying the Fourier transform twice gives you the original function reflected about the y-axis, but since this is a symmetric function, we could kind of ignore it here. Now, any periodic function that is the same thing over and over can be made up of several sinusoids at discrete frequencies, not a continuous spectrum of them. So the frequency domain looks like this. These spikes at different frequencies that represent the sinusoids that make it up, or the Fourier series, really. But this means, using that reverse operation, that if we have a bunch of spikes or samples as our original function, its frequency domain will look like a periodic function, what we just saw. So that's why this sampled discrete function has a Fourier transform that is periodic. You can think about it backwards, and it makes more sense. I'm not going to show the math of convolution in this video because I feel it needs its own, but that's how you would mathematically find this function. Essentially, sampling a signal is like multiplying it by all these samples or Dirac delta functions, and multiplying in time means doing convolution in the frequency domain, which kind of involves sliding one function against another, so that's what leads to this periodic function to infinity. But now, if someone gave you this sampled function whose frequency domain looks like this, you could apply a low-pass filter to the sampled signal and remove the higher frequencies, giving you back your original frequency domain centered at 0, and thus you could reconstruct your signal. And the reason for even doing this, like why sample at all, is because you can send those samples through a computer to do complicated stuff. If you just use the continuous signal of like someone's voice, if you want to do something to it, you need circuits, which take time to build and aren't so easy to change, whereas a computer program is very easy to change. Now, because these copies happen at integer multiples of the sampling frequency, if you sample at a slower rate, those copies start to come together until you reach a point where they intersect and combine. This is called aliasing, and that's when you lose information, because even when you apply a filter, you're not getting back the original signal. There's distortion due to the slow sampling and the resulting interference in the frequency domain. And that aliasing will happen once your sampling frequency dips below twice the highest frequency in your signal. That's where the overlap starts to happen, and if you sample slower and slower, you get more interference where these would add together, and you could not reconstruct your original signal. So now, to bring it full circle, if you were wondering how I was getting these functions before that would have the same sample values, and how we know there's nothing in between that also works, it's because of what I just showed. Here is our original cosine function, frequency 1 Hz, and here's the Fourier transform. It's two spikes really representing a single frequency of 1 Hz. It's just mirrored over the y-axis for reasons, so you actually have a spike at plus and minus 1 Hz. But now, when you sample this signal up top at, let's say, 7 Hz, to find what the new frequency domain looks like, you make copies at 7 Hz, 14, 21, and so on. Same with the negative values. So in the frequency domain after sampling, we'll find spikes at 6 Hz, 8 Hz, 13, 15, and all the numbers I showed before. That is where they come from. And if I zoom in a bit first, then we lower the sampling frequency to 1.5 Hz, the copies start to cross each other. And in this case, we're left with one frequency spike at 0.5 here, which is lower than our original signal. So that's why a lower frequency guess is valid from these samples. You didn't sample fast enough, and thus aliasing occurred. To avoid that, you need to sample at a rate at least twice that of the highest frequency in your signal. So that is the idea behind the Nyquist-Shannon sampling theorem. And if you enjoyed what you saw here, I highly recommend checking out Brilliant, the sponsor of this video. Brilliant is an educational platform home to thousands
Hmm. I did not gain the intuition for that, sadly. we learned that. There's a decimator. Make sure you can. So it just samples it every like. Okay. That frick is at 14. That doesn't sound like ideal behavior, does it? I guess it is, because these are not really numbers. They're like collections of 8 bits. Decimator 2, hold data out, right shift it by 1. So we have another one. That's something else. So I'm not too worried about that third one. Pipeline architectures. How long is this chapter, dude? 640. 660. Still at 660. 680. That's 680. 670. About to 670. So that's a lot of pages. So 1014. I'll finish this chapter skimmingly. Shortest cycle time of the clock is measure of its performance bounded by the propagation delay. The throughput is the rate at which data is supplied to and produced. Limited by the path with the largest propagation delay between primary input and register, pair between path registers, path from register to primary output, or path from primary input to primary output. Synthesis engines transform a set of two-level Boolean functions for combinational logic into a set of multi-level Boolean functions with shared logic. A circuit that results is free of redundant logic and exploits don't-care conditions to achieve a minimal description. Output functions share common internal Boolean sub-expressions. Pipeline registers can be inserted into the combinational logic data paths to partition feed-forward cut sets. Pipelining reduces the number of levels in the blocks. Combinational logic shortens the data paths between storage elements and increases the throughput of the circuit. Allowing the clock to run faster. Pipelining becomes increasingly important in high-speed wide word. Suppose the longest path through the original multi-level combinational logic has time Tmax. Multi-level 1 over Tmax. 2 blocks of multi-level logic, each having a maximum time, like 1 over 2 Tmax. Pipeline circuit can operate at this. Partition of the data math must maintain coherency. A data path for so many primary input to any primary output must pass through the same number of pipeline registers. Yes. Otherwise, you are just awaiting, bro. Cut set. If removed from the graph, isolates a node. Pipeline cut set or a feed-forward cut set is a minimum set of edges that, if removed from the graph, partitions it into 2 connected subgraphs, such that there is no path between an input and an output node. Yes. Cut sets are used, so this way you can know that you're not pipelining one thing just to delay everything else. Think. Yeah. Concepts are used to determine alternative placements of pipeline registers. The edges through which the dashed arc passes specify a locus for pipeline registers. The feed-forward cut set ensures that every path between the input. So this is the cut set. So if you cut it here, that's interesting. Removing any of the pipeline registers will destroy the concerned data. As a cost. Additional area. Additional clock routing. Not as big of a problem for FPGAs. Pipelining shortens the clock cycle, increases the throughput, introduces input-output latency. Cycle of delay. So yeah, delay. Two-stage pipeline, the effect of a transition of the input signal to after 2 clock cycles. Latency accumulates through the pipeline. It's a time shift. Latency does not alter the function. Maximum throughput is 1 over t stage. Pipelining trades spatial complexity for temporal complexity. Smaller functions and less time. Distributes across multiple shorter clock cycles when evaluated independently. 3 major benefits. Dedicated hardware performs the same single task in every clock cycle without requiring scheduling to coordinate its use among other tasks. The logic to perform a single dedicated task can be streamlined and optimized as a unit to meet constraints on performance, area, power. Data paths between adjacent stages are short and direct. Less buses. I've heard that they don't do pipe. Ours are a bit different because they still change on every edge, but just delayed by the filter length. Looking here. Alright, I'm just gonna finish this guy's issue. No, I'm not. That's probably not urgent. So looking into HDO, Haskell, or sorry, this is SV. You have the data width serially. Excuse me. So, as a bus, 8 wires. This is parallel. And that makes sense because the clock is there. Yeah, I'm kind of dumb. This is parallel. So this must be buffer. Circular buffers. Hey, I already figured that out, bruh. The algorithm's many digital filters and other signal processors repeatedly shift and store data instead of taking over a moving window. Dude, I'm goated. Should have written the book, bruh. Scheiße. Rip neck. So is the strategy to shift the samples like that one guy was doing? Yeah, okay, so these an address. So this is the shift tactic. This is the pointer tactic. I'm goated. Why am I goated? So I'm curious if there's a way to prove the amount of clock cycles this needs is 3. Because it currently takes 3. And why does it take 3? Because on the positive edge of the clock, we get the data in. That's 1. Calculate the ACC. So this happens all at the same time. So ACC. Because this depends on ACC. So maybe that should be split up somehow. I'm not too sure. FIFOs and synchronization across correct domains. First in, first out. It's a block of memory and a controller that manages the traffic data tuned from the FIFO. The reading and writing operations are similar to those of circuit with buffers, but a FIFO's architecture provides access to only 1 register cell at a time. FIFO has 2 address pointers, one for writing to the next available cell and one for reading to the next, one for reading the next. FIFOs are different from circuit buffers. FIFOs, single word, pointers for reading and writing are relocated dynamically as commands to read, write, or received, rather than continuously. You can receive data until it's full and read from until it's empty. Pointer moved after each operation has a separate address and bus data paths. FIFO above below accommodates simultaneous reading and writing of data. Usually implemented with dual port RAMs. So yeah, I know what a FIFO is. Almost full, almost empty, all that. Each channel circuit has 4 channels of serial bit streams. Serial to parallel converter. 100 megahertz. 133 megahertz. Least significant bit first. So we have this. So we're getting these into the next clock domain. So my main thing is that I don't understand how this, so this is reading faster. So that makes sense. But when it's the other way around, I don't understand how the upstream things, because like you can make the FIFO say, like the shift parallel shift register to parallel shift register say, right, stop writing. But what if it's just acting on a stream that's coming in? Like, does the stream just stop? Like, I don't really understand that. Because that's going to be the case in like this network and stuff. If the network is quicker than something running on your thing, are you just touched? When it's full, receives a write request, and it's, yeah, data loss. I think it just loses data inevitably, yeah. So yeah. I know what a FIFO is. So you're just serial to parallel. Is it wrapping a FIFO? No. Ten nanoseconds, 7.5 nanoseconds. Wait and see of 2 clock cycles. So you need a cancellation circuit. So synchronize. So this is just double D logic. That's not what it's called. Double latch. DSP. What is it called? Crossing clock domains. Double flip-flopping. Double flopping. Other name for flip-flop. Oh my gosh. Computers. Data latch. What is a D latch? D latch. D flip flop. Double flip flopping. Double flopping. I meant double flopping. I think I've been saying that wrong for a little bit. If the input stage of the synchronizer enters a matter stable state and recovers from the clock cycle. Two stages of buffering. So write to FIFO. It's controlled by the same. This. You have this mux. Always says it's 0 here. So this is going to be low. To enable this. It's connected to this. Circuit to reset. Serial parallel converters. 0 or 1. Inner structure of a dope or 5 carbon. What is the UA introduced by the block? So it's either so is it 1 or 2 or 3? I think it's either 2 or 3. Fuck, that didn't help me. Oh, because I didn't read it. Write synchronizer. So this is writing a write sync. Reset, metasync, write sync. Write to FIFO, metasync, write sync. Synchronizer 502. Synchronize to the following edge. Order race condition. Empty stack cannot be distinguished from a full stack is kind of good. read it. So this is a FIFO. Implementatia. So you got these signals, some parameters, a reg, stack status signals, assign stack full. So these are the signals, and then on the clock, reset, else if it's writing and it's not full, then we're not reading. The right pointer is data in. A stack at the right pointer is data in, and then increment the right pointer again. And read from stack. Data out, read pointer, pointer gap -1. If you're reading and you're writing and the stack is empty, just pass the data through, yeah? Oh, if the stack is empty, that means there's nothing there. So you're doing nothing. So it's effectively the same as a write. It's full, and then you're just reading. Then write to stack and read from stack, and stack not full, and stack not empty. Then data out, stack read, stack write, data in, read, write. So with sync, stack that with reg, clock write, clock read, wire, probes, two-stage pipeline to compensate for latency, neg edge, test bench, repeat 16, neg edge, read. So you have the read, these, and the right, clock read for 3, so this one's 4, so it's 133 megahertz, 100 megahertz. Okay. So there it is. There it is. And we skip the questions. Okay. So, how long is chapter 10 gonna be? Not that I'm reading it right now. So I just read from 4, so that was effectively 100 pages. Yeah, this one is another 100 pages. This one, next one will be on number representation. That's really important. Functional units for addition and subtraction. That's really important. Functional units for multiplication. That's important. Sign multiplication, fractions, division. This is really important. Then 11, post-synthesis design tasks. That's it. There's 2 more chapters in here. And a reference manual. Wow. Okay, so what time is it? So, I'm gonna brush my teeth, read, and go to bed. See, a pretty solid day. Only 2 chapters left of the massive Verilog book. It's pretty goated. We'll finish that up in the next few days. Eventually read the reference manual. Then we'll move on to the next one. We'll crank out some features on Pun Engine. And we're going to be goated. So yeah. See you guys tomorrow morning.